Dear friends, in the present video we will be discussing magnetic effect of electric current. In this part 1 we will be covering a few topics which we will be listing shortly. We recommend use of earphones for better audio quality and higher concentration. In this video we will be talking about magnet, its definition, the magnetic field and field lines, magnetic field due to a current carrying straight conductor, circular loop, solenoid. We will be discussing only the qualitative aspect of the magnetic fields and will not be dealing with the mathematical rigor, that is the strength or intensity of the magnetic field. For defining a magnet, we need to use two characteristics of magnet. A magnet is a substance which attracts magnetic substances, that is iron, cobalt, nickel, etc., towards itself and comes to rest in north-south directions when freely suspended. A single property, that is, if we say magnet attracts iron, is not enough and will not help you to identify the magnet. Recall, according to third law of motion, magnet attracts iron and as reaction iron will attract magnet. So, we will not be able to identify a magnet from that definition. Hence, we add another property, that is, it should come to rest in north-south directions when freely suspended, in addition to attracting iron, etc. Properties of magnet. First property, attracting iron, cobalt, nickel, etc., is called attractive property of the magnet. The second one is directive property, comes to rest in north-south direction when it is freely suspended. A magnet has two equally strong poles which are called north pole and south pole. The ends of freely suspended magnet point towards north is called north seeking pole or the north pole. The end of the freely suspended magnet which points towards south, which comes to rest towards south, is called south seeking or the south pole. The like poles of two magnets repel and unlike poles of the magnets attract each other. The attractive power of a magnet is concentrated at the poles and there is no attractive power in the center or middle of the magnet. The poles of a magnet are inseparable, that is, if you break a magnet into two pieces you will get two independent magnets. Each piece will have a north pole and a south pole. You cannot separate the poles of a magnet. We know that electric current produces heating effect. Electric geyser, heater, these are the devices based on the heating effect. Magnetic effect of current is another very important effect and has a number of wide ranging applications in daily life. Here in this video our concentration, our focus will be on magnetic effect of electric current. An electric current carrying wire behaves like a magnet as the current develops magnetic field around the conductor. So, electric current produces magnetic effect. Discovery of the effect shows that there is an interrelation between electric current and magnetism. The electric motor, fans, air coolers, etc., they are based on the magnetic effect of current. In fact, all devices which transform electric energy to mechanical energy, some are listed above: motor, fan, air coolers, etc. They are based on magnetic effect of current, which we will be studying in this present unit. Oersted made a significant contribution in understanding the phenomena of electromagnetism. Here, electricity and magnetism, they are interrelated, hence we coin or use the term electromagnetism. The discovery of magnetic effect was accidental. Oersted accidentally discovered that a compass needle gets deflected by an electric current passing through a metallic wire placed nearby. The observation led Oersted to the conclusion that electricity and magnetism are closely related phenomena. This correlation proved to be very important. The wide-ranging applications which we have talked above have contributed greatly to automation and influenced our daily life. It later led to technologies such as radio transmission, TV, and fiber optics. The unit of magnetic field strength is named after Oersted in his honor. We can perform an activity to study the magnetic effect of current. You have a circuit diagram. Here we connect a straight thick copper wire between points X and Y in an electric circuit as shown. The wire is held perpendicular to the plane of paper. Let's place a small compass horizontally near the copper wire XY. Note the direction of the needle. The circuit is open so far. No current is flowing. So as expected, the compass will point in north-south direction because it is always freely suspended. Insert the key into the plug and pass current through the circuit. And observe the magnetic compass. There is a change in direction of the compass needle. As soon as current is passed, the compass gets deflected. Here the current moves the magnet. If you remove the key, the compass will again go back and point in north-south direction. The deflection of the compass implies that electric current through the wire XY has produced magnetic field, confirming correlation between electricity and magnetism. So here we have seen in this activity that the current has produced magnetic field. Is the reverse effect also possible? Can magnetism produce current? We will probe it later. Can moving magnets also produce electric effect? This is an interesting phenomena to which we will come later. In this unit, we will be studying both, that is magnetic field due to current and the reverse electromagnetic effect, that is production of current using moving magnets, electromagnets, their applications, transformation of electric energy to mechanical energy, and vice versa. That is, we will study electric generator, which involves the electric effect of moving magnets. Now let's see, why does a compass needle get deflected when brought near a bar magnet? Fix a sheet of white paper on a drawing board using some adhesive material. The material should be non-magnetic. Don't use iron pins because it affects our study. Place a bar magnet in the center of the paper. Sprinkle some iron filings uniformly around bar magnet as shown. You can use a salt sprinkler for the purpose. Then tap the board gently. Iron filings get rearranged to form a definite pattern as shown in the diagram. So the magnet influences the surrounding region. The iron filings in the surrounding region experiences a force. This rearranges iron filings to form a pattern. The region of space around a magnet in which the force of the magnet can be detected is called magnetic field of the magnet. The lines along which the iron filings align themselves represent magnetic field lines. We get magnetic field lines in magnetic field, that is the space around a magnet in which its magnetic effect or magnetic force can be experienced. Alternately, we can also draw field lines using a small magnetic compass. We will now explore this alternate method of plotting magnetic field lines or magnetic field. For the purpose, take a small compass and a bar magnet. Place the magnet on a sheet of white paper fixed on a drawing board. We use some adhesive material. Avoid use of the iron pins as stated earlier. They affect the magnetic field and hence our study. Mark the boundary of the magnet. Place the compass near the north pole of the magnet at some arbitrary point marked 1. The south pole of the needle points towards the north pole N of the magnet, that is point 1. The north pole of the compass will point away from the north pole. Mark the position of the north pole as point 2. Move the needle now to a new position. After marking point 2, move the needle to the new position so that the south pole now coincides with point 2. Mark the new position of the north pole now. You can term it as point 3. Repeat the process till you reach the south pole of the magnet. Means you have to start from a point 1 near the north pole. Keep on moving the compass by continuously marking the new positions of the north pole till you get or reach to the south pole of the magnet. Join all the points that you have obtained with the help of a smooth curve. This curve represents a magnetic field line. You can now start with a fresh point like 1 new point, a different point to get a new field line. The lines give you a pattern as shown in this figure. These lines are called magnetic field lines. The field lines are used to represent the magnetic field. See, if you observe the deflection in the compass needle as you move away from the magnet, you will see that deflection of the compass needle is larger near the pole and lesser as you move away from the poles. The directions along which the compass aligns continuously changes. The change in direction indicates the change in direction of the magnetic field. In fact, a small magnetic compass is used to find the direction of the magnetic field. The direction along which the compass aligns is also the direction of the magnetic field. In fact, we say that the direction of magnetic field at a point is the direction in which the north pole of a freely suspended magnet is pointing. So, the change in direction of the compass indicates a change in direction of the magnetic field. The magnetic field has both direction as well as magnetic magnitude, that is, it is a vector quantity. We will be studying only the qualitative effect. The direction taken by the north pole is the direction of the magnetic field. By convention, the magnetic field lines are taken to emerge out of north pole and merge into south pole as marked by the arrows. Inside the magnet, the magnetic field lines point from south pole to north pole. The magnetic field lines are always closed curves. The concentration of field lines in a region measures the relative strength, that is, closer the field lines, stronger is the field. The magnetic field is stronger where the magnetic field lines are crowded. The field lines never cross each other, they do not intersect, because if the field lines intersect, at the point of intersection, the compass needle should simultaneously point in two directions, which is not possible. At a point, compass can point only in one particular direction, that is, in the direction of the magnetic field. Hence, the magnetic field lines never intersect. We know that the electric current through a conductor produces magnetic field around it. To find the direction of the field, connect a long straight copper wire, 2 to 3 cells of 1.5 volt each, and a plug key in series as shown. Insert the plug in the circuit. See the direction of current. The direction of current is from north to south in this diagram. Place the straight wire parallel to and over a compass needle. Please note, compass is under the conductor and the conductor is carrying current from north to south. Observe the direction of deflection of the north pole. The north pole will go towards east as indicated by the arrow. See the red compass, it is moving towards the east direction, that is, in this particular setup with current flowing from north to south and the conductor held over the compass, the north pole goes to east direction. Reconnect the cells now to reverse the direction of current. The current now is flowing from south to north. Please mark it very carefully. In the previous setup, current was flowing from north to south. In this setup, the current is flowing from south to north. The compass now means the north pole of the compass now gets deflected towards west. So, there is a change in direction of deflection of the needle. The needle is now moving in opposite direction as shown. It means the direction of the magnetic field produced by electric current is also reversed. If we reverse the direction of current, the direction of magnetic field produced also gets reversed. Every small element of a current carrying conductor produces magnetic field. The field due to various elements of a current carrying conductor gives us the net magnetic field. So, the pattern of the magnetic field generated by a current passing through a conductor depends on shape of the conductor. Remember, if the shape of the conductor is changed, the different parts of the conductor will reorient. If we are using a straight conductor, different parts of the conductor, they are along a straight line. If we bend the same conductor to make it into a circular current carrying conductor, the different parts, sub parts of the conductor will now arrange themselves in the circular pattern. Therefore, the magnetic field will now have a different pattern. The pattern depends on the shape in which you keep the current carrying conductor. It is different for straight conductor, circular conductor and solenoid. Let us first of all study pattern of magnetic field lines around a straight current carrying conductor. Let us take a battery of 12 volts, a rheostat, an ammeter measuring 0 to 5 ampere, plug key, connecting wires, a long straight thick copper wire as shown. Insert the thick copper wire through the center and normal to the plane of a rectangular board. Make sure that the cardboard is fixed and does not slide up and down. The cardboard should be fixed, preferably having a white paper on it. Connect the copper wire between points X and Y as shown in series with the battery, a plug and a key. Now we sprinkle some iron filings uniformly on the cardboard. You may use a salt sprinkler for the purpose. Keep the variable of rheostat at a fixed position. Record the current using the ammeter. Insert the key so that the current now starts flowing through the wire. Ensure that the wire placed between X and Y remains vertically straight. Gently tap the cardboard after sprinkling the iron filings. Observe the pattern of the iron filings. The iron filings align themselves, showing a pattern of concentric circles around the wire as shown. These concentric circles, marked blue here in the diagram, they indicate the direction of magnetic field. These circles, D circles, represent the magnetic field lines. To find direction of magnetic field, place a compass at some point P over a circle. Observe the direction of the compass needle. The direction along which the north pole of the compass is pointing gives the direction of the magnetic field lines. Mark the direction of north pole with the help of an arrow. Check the direction of magnetic field lines by reversing the direction of current. You will find that the north pole reverses its direction, indicating a reversal in direction of magnetic field. So, what is basic relation? If current reverses direction, the magnetic field also reverses the direction. Now, let us see the dependence of the magnetic field strength on current passing through the wire. For the purpose, change the current by changing the position of the rheostat or changing the variable resistance. The deflection depends on the magnitude of current in the wire. If you increase the current, the deflection in the conductor also increases. This indicates that the magnitude of magnetic field produced at a point increases as current through the wire is increased. Remember, there are two dependencies which we have talked about so far. More current, stronger field. Reverse the direction of the current, the direction of magnetic field also gets reversed. Now, let us study the effect of distance from the current carrying conductor. If you move the compass away from the conductor, keeping the current unchanged, same current, increase the distance, you will observe that there is a decrease in deflection of the magnetic compass. Hence, we can conclude that magnetic field produced by current in a conductor decreases with increasing distance from the conductor. The concentric circles representing the magnetic field become larger as we move away from the conductor. So, there are three things we sum up. The direction of field depends on the direction of current, 1. Number 2, larger the current, stronger the field. Number 3, larger the distance from the conductor, weaker is the field. Now, let us study the rule which is called right hand thumb rule to find the direction of the magnetic field due to a straight current carrying conductor. For the purpose, what you have to do is look at the diagram. The diagram is self-explanatory. Hold the current carrying conductor in your right hand such that the thumb points towards the direction of current. See red arrow, the current is flowing in downward direction. The thumb of the right hand is also pointing downward. The fingers wrapping the conductor gave direction of magnetic field lines as marked by the circle. The circle has arrows which point along the direction in which the fingers are wrapping the conductor. This is known as right hand thumb rule, and we also call it Maxwell-Cork rule. Now, what is Maxwell-Cork rule? Drive a corkscrew in the direction of the current. The direction of rotation of the corkscrew gives direction of magnetic field. The corkscrew has to be rotated along clockwise direction if you look from east. So, the magnetic field line also has been marked with arrows in clockwise direction. To reinforce our learning about the direction of the magnetic field due to a current carrying conductor, let us take an example. Here, the current through a horizontal power line flows from east to west direction, that is right to left. We have to find the direction of magnetic field directly below, that is at point Q, and directly above, that is point P. The current is given to flow from east to west direction as marked. By right hand thumb rule, if you hold the current carrying conductor in your right hand, you can see that your fingers, they are curling in clockwise direction if you see from right, and anti-clockwise direction if you see from left side or west side. So, The magnetic field is directed into the plane of paper above the wire and out of plane of paper below the wire. That is, at Q it points towards you, at P it points away from you. Here are some problems for practice to reinforce what you have learned so far about the magnetic field due to a straight current carrying conductor. Let's now study what will happen to the magnetic field if we bend the same straight current carrying conductor in the form of a circular loop. We have studied that the pattern of magnetic field lines produced around a current carrying straight wire, they form circular uh, shape. If the wire is bent in the form of circular loop, the pattern will change. We also know that the magnetic field produced by a current carrying straight wire depends inversely on the distance. That is, as we move away from the conductor, the field becomes weaker. Now, the diagram here shows a circular current carrying loop. If you take a very small element of the circular current carrying conductor, say the top of the look at the top of this circular conductor and to consider a very small element. That small element can be considered to be a part of a straight conductor. The field lines due to that very small element are circular and have been drawn in the figure. But if you move away, say you move to the center of the loop, the circle or the circular field line will become larger, the radius will increase and the line almost appears to be a straight line. Similarly, if you take the lower very small element of the conductor, due to this again at the center of the loop the magnetic field line attains a straight shape. Hence, every point on the wire carrying current now will give rise to magnetic field appearing as straight line at the center of the loop. Hence, at the center of the loop as shown, we get a linear magnetic field line. Remember, when the conductor was straight, the magnetic field lines were circular. Now the conductor is circular, so at the center the magnetic field line is now straight in shape. By applying the right hand thumb rule, we observe that at every section of the wire the magnetic field lines are in the same direction, and at the center of the circular loop these big circles appear to be straight line, they are aligned in the same direction. The magnetic field produced by a current carrying wire at a given point depends directly on the current, that is, more the current, stronger is the field. Therefore, if you use a circular wire having n turns, the field produced at the center will be n times the field that we get from a single turn. This is because the current in each circular turn is in same direction and the magnetic field due to different turns add up. To explain, if you have a single turn, the field will be say x unit. If there are 2 turns, the field will be 2x units, 3 turns 3x units, n turns nx units. In order to investigate the magnetic field further, we perform another activity. Take a rectangular cardboard, make 2 holes in it, insert a circular coil with a large number of turns through the holes. We connect the coil in series with a battery, a key and a rheostat. The rheostat is used to control the current. Sprinkle iron filings uniformly on the cardboard. Insert the plug in the key to pass the current. Tap the cardboard gently a few times and observe the pattern of iron filings on the cardboard. The pattern gives you the magnetic field due to the current carrying conductor. The circular coil behaves as a magnet with one of the faces, right or left, will act as north pole and the other will act as south pole. To find out which face acts as the north pole, you have to see that face, look at that face, say look from right hand side. If the current appears along clockwise, it will act as south face. If the current is in anti-clockwise direction, it will appear as it will become north pole. Now, let us see the magnetic field due to a current carrying solenoid. The shape of the solenoid is shown. It is a wire bound in spring shape. A coil of many circular turns of insulated conducting wire, generally copper wire we use, wrapped closely in shape of cylinder is called a solenoid. The pattern of magnetic field around a current carrying solenoid is shown in the figure. You can recall the magnetic field lines due to a bar magnet. The comparison between the pattern of magnetic field lines of solenoid and the bar magnet show that the two are identical. So, one end of current carrying solenoid behaves as north magnetic pole and the other behaves as the south magnetic pole. The field lines inside the solenoid are in the form of straight lines parallel to the axis of the solenoid. The pattern of field lines indicates that magnetic field is same at all points inside a long solenoid. That is, if the solenoid is long, practically the length should be infinite. The magnetic field lines inside the solenoid will be parallel equidistant lines, indicating that the strength of the field will be same inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material. This is in fact method by which the permanent magnets are made. We insert a magnetic material which is to be magnetized in the core of the solenoid, pass current, keep it for some time, it gets magnetized. Alternately, if you use a soft iron placed inside, you can see a rod, soft iron rod inserted in the solenoid. The magnet so formed is called an electromagnet. You have electromagnet in the second diagram. It behaves as a magnet as long as the current is passing, number 1. So, it is a temporary magnet. Number 2, the strength of the magnet depends on the magnitude of current as also the shape of the solenoid, that is number of turns in the solenoid and its radius. Thanks for being with us and watching this video. Subscribe to Physics Beckons for notifications. For feedback, you can write to the email ID on the screen.